What's up, class? In this video we will be studying a few properties of circles, figuring out the measures of arcs, and also figuring out the properties of tangent lines. The key to these types of problems is to mark up your diagrams. So the first part asks for the measure of arc DF. So the measure of arc DF, that's the arc from D to F right here. So figuring out that length, we can just simply add the 41 plus the 120, so that full length of arc DF is 161 degrees. The meaning of that is that's the angle from the center that could be connected between the center and points D and F. So 161 degrees is that central right there. Next problem, the measure from E to C to A. So E to C to A. And if we add up those lengths, we get 196 degrees. The next problem asks for arc AF. So what we could see is that if we add up all the other arcs around the circle, if we add up that list of numbers, that equals 316. 316. So 360 take away 316, we're going to be left with 44. So that extra arc right there is 44 degrees. The last problem, we're finding the measure of arc CFD. So we're adding C to F right here. And so 55 plus 44 plus 120 plus 41. So adding up that list, we'll get 260 degrees. The next problem I'm going to do just by marking up the diagram right from the get-go. Okay, so since this arc here is 36 degrees and it has two hash marks, then this is also, so that's 36. Then I know that I have a diameter AD, and the semicircle is 180 degrees because it's 360 divided by 2. So I can find AE by doing 180 take away the 36, and that equals 144. So that's that one right there. Then on the other side of the circle we have 87 and 36 and a missing piece, and all three of those pieces have to add up to 180. So 87 plus 36 is 123. So 180 take away the 123 part, and we're left with 57. So that missing part there is 57. So now that I've figured out the whole circle, I could answer the questions. The measure of arc A to E would be that shortest distance, which is 144 degrees. From A to B is the 57 degrees. C to D to B is 87. So C to D to B is basically 360 take away 36. It's just that 36 part there. So 360 take away 36 is 324. And the last one is arc BD. So arc BD is 36 plus 87. 36 plus 87 is 123. And I figured out the problem. In the next problem, I'll do the same strategy of first studying the diagram, marking up the diagram with as much information as I can, and then using the diagram to answer the questions. Okay, so it says in the directions that all the blue lines are diameters. The diameter means that the angle, for instance, from E to G right here, that whole angle there, is 180 degrees. Okay, so marking up this diagram, let's see, so I see vertical angles, so this angle there is that angle there, so that's 38. We'll have vertical angles on the other side, so that's 61. And I also have that all the straight lines, so the three angles add up to 180. So figuring out this angle right there, we'll have 38 plus 61. So 38 plus 61 is 99. And we could do 180, 99. So that is 81. So that missing angle here is 81, which means that there's an 81 on the other side. I also have that this angle here is 22, and the whole angle here is 61, so I can do 61 minus 22 and get that this missing arc here is 39. Now that I've really marked up my diagram, I will go over and look to answer the questions. So the first one, angle D to B to H, so that's that angle there, so that's 38. The next one, measure of arc HG, so arc HG right here I see is 81. That's across from angle 81. Measure of angle HBA, so H to B to A would be the 81 plus the 61. So 81 plus 61 is 142. Measure of arc DCE, so D to C to E. What I notice, DCE is basically everything except for the 61. So it's 360 take away 61, which equals 299. Arc HCF, so the H to the C to the F, that could be confusing, but we're going from H to C to F. So what we notice is we're going more than 360. So one whole circle is 360, but then we're also going this overlap distance of, or angle of 81 and the 39. So that's 81 plus 39. So if I add up that list of numbers, it'll be more than 360. So it's actually 480 degrees, which is more than a complete revolution. And our diagram is definitely pretty marked up, but for this last question, angle DBA, DBA actually marks the semicircle, so that's 180 degrees for that last question. The next question says, line GC is a common tangent to circles A and B. So this line GC is a common tangent to circles A and B. Explain why triangle GBD is similar to triangle GAC. So looking into this. Line GC is a common tangent because a tangent line is a line which hits the circle only once. So from our prior lesson, what we can do when we have a tangent line is we can draw in the right angle between the tangent line and the radius. So that's this right angle here. So what the question is saying is, why is the triangle GBD, why is that right triangle there similar to triangle GAC? Saying that So we have the smaller triangle and the larger, proportionally similar triangle. Okay, and explain why these are similar. Okay, so when we look at the diagram, what we do have is we have this reflexive angle G. So that's an angle in both triangles. So therefore, both triangles are similar because of the angle-angle similarity property. And what that implies is that, for instance, side GD here is over side GC here is equal to side GB here over GA here. We can draw up those proportions. The next problem, we're given that AB is a tangent, so we can automatically draw in that right angle right there. And we're looking for X right here, which is CB. Okay, so marking up the diagram, if I just look at the triangle there, then I have 90 and 45, so the other angle is 45. So since we have a 45, 45, 90, that says that this triangle is isosceles, which means that the whole other side has to be 10. So since that whole other side is 10, then that side is the diameter. That means that both sections here must be 5, and side CB is equal to 5. So we have that CB is equal to 5. The next problem, we're looking for side AC. So we have our tangent line, so we can draw in our right angle. That's the key concept from the lesson, is whenever we have a tangent line, we can draw in our right angle between the radius, this radius, and the tangent line. Okay, so now we're looking for side AC. So we can see that we have our right triangle, so we can do the Pythagorean theorem. A squared plus B squared is C squared. So we have 15 squared plus 8 squared is C squared. So 225 plus 64. If I add those up, then that is 289. C squared. So C is equal to, squared is 289, which is 17. So side AC has to be 17. So that answer there is 17. For the next problem, it looks like we're looking for side CB. So I'm marking that on the diagram. We're looking for this side here, CB. Okay, so the radius of the circle. Taking a look at it, okay, so we have our tangent line. We could draw on that right angle. So what I notice is we have an angle and a side. So we could find missing sides using SOHCAHTOA. So labeling, it looks like this particular problem uses the opposite and the adjacent sides. We're not using our hypotenuse. Okay, so we'll use tangent. So tangent 55 is equal to 9 over x. When we cross multiply, we'll get 9 equals tan 55 times x. So dividing by tan 55, x equals 9. Divide by tan 55. So on a calculator, that equals 6.3. So the missing side is 6.3, and that's our radius of our circle. Let's take a look at that last problem. Okay, so for this last problem, we're looking for side FA. Okay, so first step, by now we got it. We have our tangent line. We draw on our right angle. So that means we can use Pythagorean theorem or SOHCAHTOA for these problems. So I could find in that right triangle, I could find the hypotenuse. And actually, we have sides 6 and 8, so it's a 3, 4, 5 triangle. 3, 4, 5, 6, 8, 10. So the whole side is 10. I might be tempted to think that both of those sections are 5, but the key is to mark up the diagram that the radius is 6. So that means that the radius here is 6. So that missing section has to be 4 in order to add up to 10. So section FA is 4. The next problem, we're looking for side AB right here. Okay, so we have our tangent line. We'll mark our right angle between the radius and the tangent line. Okay, so marking up the diagram, the radius is 5, so I'll mark this 5 right there. And then the whole hypotenuse is going to be 13. So looking at that right triangle, we have 5 and 13, so the missing side has to be 12 because it's a 5, 12, 13 triangle. So that's a Pythagorean triplet, just like a 3, 4, 5 triangle. We could also use the Pythagorean theorem to get that side is 12. The next problem, we're looking for side CB right here. Okay, so marking up the diagram, we have our right angle. Here's our tangent line. So then 12 is this whole distance of the hypotenuse of the right triangle. And we have 30 degrees. So we could use SOHCAHTOA to get the missing sides, or we could use the fact that it's a 30, 60, 90 triangle. So since it's a 30, 60, 90 triangle, and we're given the long side is 12, so we could go from long to short, and to do that we divide by 2. So that means this short side is 6, and then we can go short to medium, so that's multiplying by square root of 3. So the whole diameter of the circle is 6 radical 3. So if that's the whole diameter, then the radius would be 6 radical 3 divided by 2. So 6 radical 3 divided by 2 is 3 radical 3. So that's the radius, 3 radical 3. This problem here, we're looking for the radius CB right there. Okay, so we have our tangent line, so we can mark the right angles. In marking those right angles, what I see is this is one of those fancy cases where we have 3 triangles, and all 3 of those triangles are similar to each other. We have that triangle right there, that triangle right there, and the large whole triangle. Okay, so because of this, then we have special patterns of proportionate sides. So we could say short to medium on the one triangle is short to medium on the other triangle. So doing that pattern, 2 to x on the left triangle is equal to x to 4 on the right triangle. Going further, we could cross multiply. 8 equals x squared, so square root of both sides, and x equals the square root of 8, which is approximately 2.8 rounded to 1 decimal place. In this problem, again, we're looking for the radius CB right here. So what I notice is that's the same as that radius here, which is the same as that radius there. Filling in my right angle right there. Okay, so if I redraw this triangle right here, what I can see is that they're in a proportion of x to 2x to 10 radical 3. So what that implies is the pattern of a 2 and a radical 3, which means that x is 10. Because then as a 30, 60, 90 triangle, then if x is 10, it would be in a proportion of 10 to 20 to 10 radical 3, which is the 30, 60, 90 pattern. Here's the last problem that we'll have time to do today. Okay, so here's our right angle, and we're looking for CB. That's the radius, so I'll mark both of the radii as x. Okay, so applying the Pythagorean theorem, a squared plus b squared equals c squared, we'll have x squared plus 15 squared is equal to this whole side, which is x plus 9 squared. Okay, so going further with that, we have to simplify that x plus 9 squared. So the surprise is that it's not x squared plus 81. If we draw this out with our Punnett square earlier, then this is x plus 9, x plus 9. So multiplying those boxes, we have x squared plus 9x plus another 9x here, and 9 times 9 is 81 there. So we'll have x squared plus 18x plus 81. Okay, so that's right here, x squared plus 18x plus 81. And that's equal to x squared plus 225. So going further in this problem, first thing I notice is I could minus x squared to both sides. Those x squareds go away. So really I just have a simple linear equation to solve. 225 is equal to 18x plus 81. So take away 81 from both sides. 18x is 144. So dividing by 18, then x is equal to 8. So we were able to get that the radius of the circle has to be 8 in order for this to be a right triangle right there.